Chapter 2, Section 3, the Rational Zeros Theorem. This is going to be a super helpful theorem for us when we're trying to find the zeros of a polynomial function. Now, what we've discovered in the previous lesson is that any polynomial function with degree n greater than or equal to 1, so n stands for the degree of the function, will have exactly n zeros, provided each zero is counted using its multiplicity. So we found that a cubic polynomial, which is degree 3, has 3 zeros. We found that a quartic polynomial function, which is degree 4, has 4 zeros, as long as you're counting each zero using its multiplicity. All right, so that's where we kind of left off in the previous lesson. All right, guys, here's the Rational Zeros Theorem. I know it's pretty lengthy, but I will walk you through it. I'll walk you through all of this very mathy language, okay? If f of x equal to a sub n, x to the power n plus a sub n minus 1 times x to the power n minus 1 plus etc. plus a sub 1 x to the power 1 plus a sub 0 is a polynomial function with integer coefficients. So the coefficients, a sub n minus 1, all of these a's, they're coefficients, and they're saying that they're only integers, which means positive and negative whole numbers. And the leading coefficient a sub n, there, I just fixed it. That should be a subscript. The leading coefficient is a sub n. It's way up here in the front. That's the leading coefficient, is not 0. And the constant term a sub 0, that's this last term. It's just a constant. There's no variable. Then this is the powerful part. Any rational zero of f of x. Now, a rational number is a number that can be written as a quotient of two integers. Or plainly put, you can write it as a fraction. Any rational zero of this function f of x will be in the form p over q. P over q, where p is a factor of the constant term a sub 0, and q is a factor of the leading coefficient a sub n. Okay? I think it might be easier to understand what all of this means if we look at a concrete example. All right? So let's jump into an example. All right, guys, check this out. Use the Rational Zeros Theorem to create a list of all of the rational numbers, so all the fractions, that may be rational zeros, keyword may be, rational zeros of this cubic polynomial function. Now, let's be clear what the Rational Zeros Theorem says. It says that any rational zeros of this function must be of the form p over q. P over q. Now, p, if you read the theorem, is a factor of the constant term. Your constant term here is 10. So the factors of 10 are plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. The q here, the denominator, are factors of the leading coefficient. The leading coefficient is 3. So the factors of 3 are plus or minus 1, plus or minus 3. So these quotients here give you all of the possibilities when it comes to rational zeros for this function. So now all we have to do is simplify. Let me move the screen up, okay? So that's what it means, the Rational Zeros Theorem. Now let me help you simplify. Now, what I do here is I write each one of these numbers in the numerator, each one of these factors, over 1. And then I'll write all of the numbers in the numerator over 3. So first, when I write them all over 1, I get plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 5 over 1, plus or minus 10 over 1. That's just the list of the numerator factors over 1. Now I got to do all the numerator factors over 3. So plus or minus 1 over 3, plus or minus 2 over 3, plus or minus 5 over 3, finally plus or minus 10 over 3. Now that you have your list, you should simplify this. So you have plus or minus 1, 2, 5, and 10. 2, 5, 10, comma, plus or minus 1/3, plus or minus 2/3, plus or minus 5/3, plus or minus 10/3. This, ladies and gentlemen, is the full list of your possible rational zeros, all right? Now, there are a lot of options here, a lot of possibilities. What, 1, 2, 3, 4, 8 times 2, because of the plus or minus, 16 different possibilities for rational zeros for this function. Now, let me be very clear. The theorem does not say that the function they gave us has to have a rational zero. That's not what we're saying. We have no guarantee that the function they gave us, let me scroll back up so that you can see it on your screen. We have no guarantee that this function has any rational zeros. But what we do know is that if it has any rational zeros, those zeros must be in this set, must be in this list somewhere. Is that clear? Again, one more time. We're not guaranteed that the given function has any rational zeros at all. But if it does, that rational zero has to be inside this list. All right, let's try it again to make sure we understand, okay? So, if this function has any rational zeros at all, then they must be of the form P over Q. P over Q. All right. Now, remember P stands for the factors of the constant term. The constant term here is 12. So let's list all the factors of 12. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Now, Q stands for the factors of the leading coefficient, which is 2. So plus or minus 1, plus or minus 2. All right? So now we have to break this up. So I'm going to list all of the factors in the numerator. I'm going to list them all over 1. And then I'll list them all over 2. All right? So let me put them all over 1 first. Plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 4 over 1, plus or minus 6 over 1, plus or minus 12 over 1. Now, put them all over 2. Plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 3 over 2, plus or minus 4 over 2, plus or minus 6 over 2, plus or minus 12 over 2. Wow, that was fun. All right, now what we should do is simplify all of these numbers. So the first row, whenever you divide a number by 1, the quotient is that number. So the first row is just plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. The second row would be plus or minus 1/2. Watch this. Plus or minus 2 over 2 is where I'm at, and that is 1. Plus or minus 3/2, plus or minus, I'm right here, 4 over 2, which is 2. Plus or minus 3, and then plus or minus 6. I want you to notice the duplicates. There's 1 in this list twice, so I don't list duplicates. 2 is listed twice, 3 is listed twice, 6 is listed twice. So you do not list any duplicates. So all of the possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12, plus or minus 1/2, plus or minus 3/2. This is the complete list of possible rational zeros. Possible rational zeros. So once more, I'll explain this. If the function has any rational zeros, we're guaranteed that they have to be in this list. All right, let's go back to example 1. We looked at this function in example 1, and we used the Rational Zeros Theorem to come up with this list of possible rational zeros. By the way, everybody, if you do not want to write the plus or minus symbol over and over and over and over again, you can write it outside of the set notation, and that'll be fine. Now, the Rational Zeros Theorem says that if this cubic polynomial function has any rational zeros, then they have to be in this list. So what we're going to do now is use the remainder and factor theorems from the previous lesson to start checking these, and we want to check to see which one of these, if any, happen to be zeros. So what I'm going to do is I'm going to set up synthetic division. The first value that I want to check, the first possible rational zero that I want to check is 1. That's the first entry in my set, right? So the synthetic division focuses on the coefficients of your function, right? So we did this a lot in the previous lesson. So you have these. Now, I'm going to set this up. All right. Now, everybody, if the remainder turns out to be 0, then our conclusion is 1 is a zero of this function. If the remainder is not 0, then we say 1 is not a zero of the function. All right, so you know how this goes. Drop the 3. 1 times 3 is 3. Negative 20 plus 3 is negative 17. 1 times negative 17 is negative 17. 23 minus 17 is positive 6. 1 times 6 is 6, and 10 plus 6 is 16. Now, because this is not 0, we know that 1 is not a zero of this function. All right, so what we'll do is we will try a different number. So 1 didn't work out, but there's plenty more options. All right, so the next value I'm going to try, and you can try these in any order, I'm going to try -1. All right, let's see if this works. Drop the 3. -1 times 3 is -3. Negative 20 plus -3 is negative 23. -1 times -23 is 23. And this is 46. I don't think this is going to work. -1 times 46 is negative 46. And this gives me negative 36. All right, so then this is not 0. Therefore, -1 is not a 0 either. All right, so far we've gone through 2 different values, and neither of them worked. Neither of them turned out to be a 0. You got to keep on going, okay? So let's try, should we just go for the number 2? That's next in the list, so why don't we go for that? Okay, so let's drop the 3. 2 times 3 is 6. Negative 20 plus 6 is negative 14. 2 times negative 14 is negative 28. 23 minus 28 is negative 5. Oh, look at this. 2 times negative 5 is negative 10. And then this is 0. Awesome. So we just found a 0 for our function. All right. So do you remember from the previous lesson that here this represents your quotient? And we also mentioned that the quotient is 1 less degree than where you started. So we started with a cubic polynomial. So these numbers here represent the coefficients of a quadratic or degree 2 polynomial. So this is what we have, everybody. The factor theorem says that if 2 is a 0, x minus 2 is a factor. You may need to reread what the factor theorem says, but that's basically what it says in a nutshell, that if 2 is a 0, then x minus 2 is a factor. So this is what we have so far, everybody. Our function can now be rewritten like this. X minus 2, that's because 2 is a 0, times this second degree polynomial. So it'll be 3x squared minus 14x minus 5. All right, and now maybe we can use, maybe we can use at this point our factoring techniques to factor further, if it factors further. If it factors further, it'll factor like this. And this would have to be -5, yes, and +1, like that. So you and I just fully factored. We completely factored our function. All right? We completely factored our function. Can you tell me what the zeros are now of our function? Can you tell me what the zeros are? I hope you're thinking, well, I would take each of my factors, set them equal to 0, and solve. So this one, after adding 2 to both sides, you get x equal to 2. This one, you would subtract 1 from both sides, and then divide by 3. And this one, add 5 to the right. Okay, so you found all 3 zeros. Remember, it was a cubic degree 3 polynomial function, and we found 3 zeros, all right? So these are the 3 zeros of your function, written in set notation, 2, comma, -1/3, comma, 5. Okay, that's what it is. By the way, each one of these has multiplicity 1. All right, cool. I hope you guys are having fun. Now let's go back to example number 2. Example number 2, we were looking at this function here. We used the Rational Zeros Theorem, P over Q, to get this list of possible rational zeros. All right, let's start going through this list, and let's see if you and I can stumble upon a zero using synthetic division. All right, let's start with the number 1. All right, so using synthetic division, I'm checking the number 1. My coefficients are 2, -3, -24, 13, and 12. Now, drop down the 2. 1 times 2 is 2. -3 plus 2 is -1. 1 times -1 is -1. -24 minus 1 is -25. 1 times -25 is -25. 13 minus 25 is -12. 1 times -12 is -12. And we get 0. Awesome. We just found a 0. 1 is a 0. So what I'm going to do is I'm just going to put like a big star here, right? Or a happy face or something, okay? Because 1 is a 0, we know by the factor theorem that this implies that x minus 1 is a factor. Okay, everybody. Let's keep going because this is degree 4 in the beginning. That means this is degree 3, right? 1 less than what you started. So because we're not down to degree 2 yet, because we don't have something quadratic yet, I'm going to continue with synthetic division. All right, everybody? So we started at degree 4, and so now we're at degree 3. The basic rule of thumb is continue doing this synthetic division until you get something that is at least, or at most rather, degree 2. So stop maybe once you get to degree 2, okay? So I'm going to keep going. Now, let me move up here a little bit here. What I'm going to do is, maybe about right there. What I'm going to do is try a different value. Remember, I am going to use these coefficients now, the brand new coefficients of the, it's called the reduced or depressed polynomial. Now, I actually said something wrong. I just finished saying I'm going to try a different value. Actually, that's not true. I'm going to try the same number again. Why? We just figured out that 1 is a 0, right? I did it. Why am I doing it again? Well, I'm checking for multiplicity. If 1 turns out to be a 0 again, that means it has multiplicity 2, right? So right now, I'm checking 1 again to see if it has multiplicity of more than 1. All right? All right, drop the 2. 1 times 2 is 2. Negative 1 plus 2 is 1. 1 times 1 is 1. Negative 25 plus 1 is negative 24. 1 times negative 24 is negative 24. This is negative 36. All right, 1 is not a 0 again, right? So it was just a 0 one time. So I'm just going to do this, guys. A big X right there, okay? It didn't work out again. No worries. Now let's move on to a different value from our set list. Where's our set? It's up here. So we tried positive 1. How about we try negative 1? All right, everybody. Let's try negative 1. This is a great place to pause the video and to use synthetic division on your own and check to see if negative 1 is a 0. I found that negative 1 is not a 0 because the remainder is not 0. Let's try a different value. How about the number 2? Because 2's in the list. All right, everybody, give this a shot on your own. Check to see if 2 is a 0. I hope you found that 2 is not a 0. All right, got to try a different value. How about negative 2? All right, so try negative 2, everybody. Go ahead and pause the video again and try negative 2. All right, I hope you agree with me that that did not work either. So we're not getting lucky here. Let's go to a different value for my list. I honestly forgot what my list looks like. Let's go back up. Here we go. So we've tried 1 and 1 worked. Negative 1 did not work. 2 did not work. Negative 2 did not work. Let's try 3. All right, go ahead and try 3 and see if it works. Pause the video, please. All right, 3 did not work either. Whew, all right, got to keep on going. Don't give up, guys. Let's be persistent. Let's try negative 3, I guess. All right, I got negative 3 set up. Why don't you pause the video again and give this one a shot. Finally, we stumbled upon another 0, right, everybody? Whew, all right. Because negative 3, be careful here. Because negative 3 is a 0, the factor theorem says that, so that's the implies, that x plus 3 is a factor. Okay, x plus 3 is a factor. Be careful with your signs, okay, everybody? All right, so we have 2 factors. Now watch this, everybody. This is now degree what? Have you kept track? We were at degree 3. Now we're at degree 2. Because this is degree 2, I'm going to stop this synthetic division business. I don't have to do this anymore. And so what I'll do is I'm going to say, all right, my function, which is up here, remind you, it's g of x, right? And I also want to remind you while I'm at it, I didn't want to move that. I also want to remind you that, let's see, here it is, x minus 1 is a factor and x plus 3 is a factor. All right, so let us now rewrite the function. G of x is equal to x minus 1 is a factor, x plus 3 is a factor, times, times this quadratic right here, this quadratic, 2x squared minus 7x minus 4. Isn't that great? So synthetic division helped us get this, factor and this factor. And then this is what remains. Let's factor this if we can to get the last 2 factors, all right? Let me move this up here. So then this here, let's see if it factors further. Let's just copy all this down here. All right, here we go. If it factors further, it has to factor like this. Let's see, it would have to be 2x times 1x. And we would want -4 and then plus 1. That's how it must factor. Now since this function, which was a quartic, wasn't it a quartic polynomial function? It has now been fully factored. Can you tell me what your zeros are? Well, sure you can. You would set each factor equal to 0 and solve. All right, this one, add 1 to the right. This one, subtract 3. This one, subtract 1 and then divide by 2. And this one, add 4. So in set notation, it'll be 1, -3, -1/2, and 4. All right, those are all of my zeros. All right, everybody, you can see that in the previous example, it took us a while to stumble upon the zeros for that function. We did synthetic division over and over and over again. So you can see how we are very interested in any kind of resource that would help us shorten that list that the Rational Zeros Theorem gives us. That is what Descartes' Rule of Signs is used for. Descartes' Rule of Signs sometimes it shortens the list that the Rational Zeros Theorem gives us as possibilities. This is how it works. Let f of x be a polynomial function with real coefficients and terms in descending power order, okay? Here it is. The number of positive real zeros is the same as the number of sign changes in your function, or is less than this number by a multiple of 2. The number of negative real zeros is the same as the number of sign changes in f of -x, or is less than this number by a multiple of 2. So basically, Descartes' Rule of Signs is telling you how many possible positive zeros you have and how many possible negative zeros you have. All right? I should say positive real and negative real zeros. Here's an example. All right, let's use Descartes' Rule of Signs for this example. Use Descartes' Rule of Signs to determine the number of possible positive and negative real zeros for this cubic function. All right, so let's first talk about how many possible positive real zeros, right? So this is for positive zeros, okay? For positive zeros only. Now, the theorem says all we have to do is count the number of sign changes. Sign changes is when the sign changes from positive to negative or negative to positive from term to term. So I want you to look at your function f of x. And the first term is positive, the second term is negative, the third term is negative, and the constant term is positive, right? Those are these signs here. Let's count the sign changes. This is a sign change, and this is a sign change. So there are 2 sign changes. So the Descartes' Rule of Signs says the number of positive real zeros is the same as the number of sign changes, or less than this number by a multiple of 2. So then what I know right now is that there are 2, because there's 2 sign changes, there are 2 or, right here it says less than this number. That means I need to subtract. Subtract this number of sign changes I just counted. Subtract that by a multiple of 2. In other words, 2 minus 2. 2 is the multiple of 2. This 2 is from how many sign changes I counted. So 2 minus 2, of course, is 0. So these are your options for positive zeros. For positive zeros, let me write out the word positive. Positive real zeros, you either have 2 or none at all, right? Either 2 positive zeros or 0 positive zeros, okay? So either you have 2 positive zeros or you don't have any at all. Let's now count how many negative real zeros there are for this function. It says that we have to count the number of sign changes in f of negative x. All right, so what I have to do is substitute negative x into this function. Now, I want you to notice something. This first term is being raised to an odd power. If I substitute negative x in here and raise negative x to an odd power like 3, then this whole term is going to change its sign. Right now it's positive. It'll turn negative. That's because its power was odd. Here, the power on x is 2, which is even. So if I let x be negative x, right? That's what this says to do. Negative x squared is the same as just positive x squared, right? Negative x squared is just going to be a positive value because you're raising it to an even power, which means this term will just keep its original sign, which is negative. The next term, if you substitute negative x for x, you're going to have negative 3 times negative x, which will give you a positive. And then the last term is just positive 8. All right? Let's count our sign changes. This is a sign change. Oh, and that's it. So you only have one sign change. That means you only have one negative real zero. That's it. One negative real zero. Now, I want to mention something here. It says is the same as the number of sign changes in f of negative x, or is less than this number by a multiple of 2. I'm not going to bother subtracting by a multiple of 2 here like I did a little while ago for the positive zeros, because if I do, watch this, 1 minus 2 is negative 1. I can't have negative 1 number of negative real zeros, right? So I won't even bother subtracting by a multiple of 2 for this example. All right, let's try it again. Example 4, let's use Descartes' Rule of Signs to determine the number of possible positive and negative real zeros for this quartic polynomial function. All right, let's start with positive zeros, all right? I'm going to write the word positive. Now, what I need to do is count all of the sign changes in my function. Now, I notice that in my function f of x, the first term is positive, the next term is negative, and then positive, positive, and then negative. So then when I count the sign changes, I count 1, 2, 3 sign changes. So Descartes' Rule of Signs says that's exactly how many positive zeros you're going to have, or less than that number by a by a multiple of 2. So you will either have 3 or 1 positive zero. Those are your options. Now let's talk about negative zeros, okay? Now for negative zeros, negative real zeros, we have to count the number of sign changes in f of negative x. Now, the first term, the variable has an even exponent. So no matter what you plug in for x, and actually here we're plugging in negative x for x, negative x to the 4th power will be the same thing as just x to the 4th power. So this term will keep its original sign, which is positive. The next term, the variable has an odd exponent. That's going to make this term change sign. So it's negative right now, it'll become positive. The next variable has an even exponent. That means it's going to keep its original sign, so it'll stay positive. And then here, when you let x be negative x, it turns this whole term negative. And then the last term is negative 12. Okay, so when I count the sign changes, I only count 1. So there will only be 1 negative real 0. See, this is helpful because if I were to ask you to find the zeros of this polynomial function, and let's say you're using synthetic division and you come across a negative 0, then you can guarantee yourself that that's the one and only negative real 0, and you don't have to search for any more negative zeros. All right, let's jump to example 6. Describe the possible cases for the zeros of this function. Okay, let me walk you through what they mean by this. Let's determine, using the Descartes Rule of Signs, let's determine the number of possible positive real zeros. Now, the way we'll do this is by counting the sign changes. I see positive, positive, negative, negative, right? So when I count the sign changes, I only count one sign change. So there will only be one positive real 0. That's helpful. Now, when we consider negative real zeros, we have to count the sign changes in g of negative x. When I substitute in negative x, here it turns this term negative. It causes this term to keep its original sign, so it's positive. It turns this term positive, and then the last term is constant at a negative. So counting the sign changes, I have 1, 2 sign changes, so then I'll either have 2 negative zeros or 2 minus 2, which is 0, right? So as far as negative zeros go, I either have 2 or I have none at all. So these are my options for your zeros, okay? I guess I should have written the word or right in the middle here, okay? So either you have 2 negative zeros or none at all. All right, let's describe the possible cases for the zeros of this polynomial function. Now, before I scroll down to create more room, I want you to notice that the degree of this function is 3. Okay, that means you have 3 zeros all together. 3 zeros all together. All right, here we go. Now, I created this table here. This first column is for how many positive zeros you have, positive real zeros. This is how many negative real zeros. These are your non-real zeros, so think of these as imaginary, okay? And then the total number of zeros. Now, let's talk about this first case. Now, let me scroll up here. Remember how many positive zeros you have? Only 1. So I'm going to put in 1 in this first column here. Remember, there has to be 3 zeros altogether. And then Descartes' Rule of Signs says that you could have 2 negative zeros. Now, if you have 1 positive 0 and 2 negative zeros, 1 plus 2 is 3. That's it. That's all. That's the total number of zeros. That leaves you with 0 non-real. Okay. Another option is to have 1 positive 0 and no negative zeros. That must mean the other 2 zeros are imaginary or non-real. So when you add these together, 1 plus 2 is 3. So this is what they mean when they say describe the cases or find the cases for the zeros of the function. These are the different cases. Check out this new example. Example 7, factor this function, a cubic polynomial function, and determine its zeros. All right, to get us started, we're going to use the Rational Zeros Theorem. For short, sometimes I do RZT for Rational Zeros Theorem. And remember that it tells you that if this function has any rational zeros, they'll be of the form P over Q. Now don't forget that P represents the factors of the constant, which is 14. These are the factors of 14. And Q represents the factors of the leading coefficient, which happens to be 1, thankfully, because that's going to just be 1 down here. So then all of your possible rational zeros are plus or minus 1, 2, 7, and 14. Now notice that you have 1, 2, 3, 4, 4 times 2. You have 8 options or 8 possibilities altogether. Of course, those are just your options for rational zeros. Now I want you to recognize what Descartes' Rule of Signs says. Notice that all of the terms in this function, all of them are positive. So it's like this: positive, 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 positive. There are no sign changes in this function. No sign changes. So what does that mean? No sign changes in f of x. That means, since there are no sign changes, that means you will not have any positive real zeros. No positive real zeros. So actually, if I can scroll back up here, if I know that I will not have any positive real zeros, that cuts this list in half. I can toss out all of my positive numbers. So my new list, so I'll put my new list, right? My new list will not include any positive numbers. So it'll be just -1, -2, -7, and -14. So instead of having 8 options or 8 possible rational zeros, I only have 4. See, this is going to save me a lot of time. So now I'm not going to waste my time even checking any positive numbers because they're not going to work. Okay, so now let's use synthetic division and see which one of these is a 0, if any at all. All right, so I'm going to check -1. My coefficients in my function, they're up here. Let me see if I can scroll back up for us. Here it is. 1, 4, 11, 14. All right, and I'm going to use synthetic division to see if -1 is a 0. All right, here we go. Drop the 1. -1 times 1, -1. This is 3. I hope you feel real confident with this process. So this didn't work, everybody. I did not get 0 as a remainder, so let's try -2. All right, so you can pause the video here and try this on your own. I hope you got it to work as I did. So -2 is a 0. If -2 is a 0, that means x plus 2 is a factor by the factor theorem. All right, everybody. So -2 is a 0 and x plus 2 is a factor. Now the original polynomial was degree 3. That means this is degree 2, right? The quotient is degree 2. So this is what I would like to do. Your function, let's see, your function, what was the name of your function? Do you remember? It was, let's see, there it is, f of x. So f of x, if I could just do this here, f of x is now equal to x plus 2 times this degree 2 polynomial, which says 1x squared plus 2x plus 7. Now, the instructions said to factor the polynomial and then find its zeros. Now, this is quadratic. This does not factor any further. So you have answered the first part of this problem. You have factored, you have factored the polynomial. Okay, that's as far as you can go as far as factoring. Now, to find the zeros, what you will do now is set each of these factors equal to 0 and then solve. Now, this second factor here, this trinomial factor, x squared plus 2x plus 7, does not factor, so we'll use the quadratic formula. Here, we'll subtract 2 from both sides, and get x is equal to negative 2. All right, so there's one of your zeros. For the quadratic formula, we'll get x is equal to negative and then positive 2 plus or minus the square root of 2 squared minus 4 times 1 times 7. This is the quadratic formula, all over 2 times 1. So then x would be equal to negative 2 plus or minus the square root of 4 minus 28. And then all of this is over 2. We need to move down here. And then this means x is equal to negative 2 plus or minus the square root of negative 24 all over 2. Now, a lot of simplifying here. Let's see. 24 can be rewritten as a product of two factors where one of them is a perfect square. You can rewrite the square root of 24 as the square root of 4 times the square root of 6. And you're going to have I show up because the expression underneath the radical has a negative sign. So then this becomes x is equal to negative 2 plus or minus 2I root 6 all over 2. Now everything is divisible by 2, so I want you to divide this 2 into this 2 and into that 2, right? And so you're left with x is equal to negative 1 plus or minus 1I root 6. All right, everybody, I think we found all of our zeros. So these are two different complex solutions or zeros, and then the other zero was here, x equal to negative 2. So let's write down all of our zeros in set notation, okay? So negative 2, and then you have negative 1 plus I root 6, and you have negative 1 minus I root 6. Those are your zeros. Okay, everybody, let's tackle this problem. Factor this function and determine its zeros. All right, so first things first, Rational Zeros Theorem. Let's get that started. All right, so we've figured out what P over Q is. Remember, P are the factors of 27 or negative 27, and Q are the factors of the leading coefficient, that being 2. I'll put all of my factors in the numerator over 1, and then I'll put them all over 2. All right, when I put them all over 1, I just get 1, 3, 9, 27. And then when I put them all over 2, I get 1 half, 3 halves, 9 halves, and 27 halves. Here's the formal notation for all of my my possible rational zeros. Right here it is. I put plus and minus symbol on the outside here, and you got a lot of options, right? So let's see how many options. 1, 2, 3, 4, 5, 6, 7, 8 times 2, 16 different possibilities for rational zeros. Let's see if Descartes' Rule of Signs cuts this list down some. All right, so Descartes' Rule of Signs. One thing I notice is that the terms that have odd power, so this term here and this term here, are the same sign. They're both positive. And then this term here that has even power is the opposite sign. It's negative, and the constant term is also negative. What that leads me to inspect is g of negative x, which will tell me how many negative real zeros I have. Now, when I consider g of negative x, the first term is negative, the next term stays negative, the third term becomes negative, and the last term is always negative. So what I see right away is there are no sign changes in g of negative x, which leads me to the fact that there are no negative zeros. Now, this is fantastic news, because what that does is it takes this list and cuts it in half. Take out all of the negatives. All right, everybody, here's my updated list. I just took out the plus or minus symbol, and now I only have positive possibilities for rational zeros. Now here we go. We're going to start checking these possibilities using synthetic division. Let's start with the number 1. And my coefficients of the function are 2, -9, 18, and -27. Now positive 1 did not work, so I'm going to move on to the number 3. Okay, I have it all set up to check 3. Now I will check this using synthetic division. And we have a winner. So 3 is a 0. That means x minus 3 is a factor. And this is by the factor theorem. Now, please notice that your original polynomial is degree 3. That means this here is degree 2. This is degree 2, all right? So then our function can be rewritten as follows. G of x is equal to, we have one of our factors here. This here is quadratic, it's degree 2. So then it's 2x squared minus 3x plus 9. So we have factored completely. This doesn't factor any further. You can try, but it does not factor any further. So I'm going to go ahead and box this. This is the complete factorization of our polynomial. Now the other instructions, the second half of it says determine the zeros. So now you and I know that all we have to do is take each factor, set it equal to 0, and solve. Now because the second trinomial factor here does not factor, we'll use the quadratic formula. So we'll get x is equal to positive 3 plus or minus the square root of negative 3 squared minus 4 times 2 times 9, and all of that over 2 times 2. Over here on the left, once we add 3 to the right side, we're done. That's one of your zeros there. All right, we have to simplify this, so this becomes 3 plus or minus the square root of 9 minus 72 all over 4. Okay, let's continue simplifying. So then we end up getting x is 3 plus or minus the square root of negative 63 all over 4. And I can rewrite 63 as a product of two factors where one of them is a perfect square, namely 9. You have an I because the expression underneath the radical, it's called the radicand, is negative. And then the denominator is 4. So then these complex solutions are 3 plus or minus 3i root 7 over 4. And I'm going to write each term over 4 like that. Okay, that's called standard form for a complex number. All right, so we have found all 3 of our zeros. All right, we will use set notation to write all of our solutions, our zeros. So one of them is 3, and the other ones are 3/4 plus or minus 3i root 7 over 4. There's 3, and each one of these has multiplicity 1. All of them have multiplicity 1. They all appeared only once as a solution to the polynomial. All right, good job, you guys. The last theorem of this section, and the last part of this section as well, is called the Boundedness Theorem. And this theorem, like Descartes' Rule of Signs, it sometimes shortens the list of possible rational zeros provided by the Rational Zeros Theorem. So it cuts down your possibilities. But unlike Descartes' Rule of Signs, the boundedness theorem is actually applied after every synthetic division has been performed. This is what it says. Let f of x be a polynomial function of degree n, which is greater than or equal to 1, with real coefficients. Now here it is, divided by a factor like x minus c. This is a linear binomial. As I was reading this, folks, I noticed that the word function was missing, so I added that. Now here we go. If c is a positive number, okay, and every number in the bottom row during synthetic division is non-negative, then c is called an upper bound for all the real zeros of f of x. I'll talk to you in a minute about what this means. If c is negative and the numbers in the bottom row during synthetic division alternate in sign, meaning plus, minus, and so forth, with 0 being considered as either positive or negative as needed, then c is called a lower bound for all the real zeros of f of x. Let me show you what all of this means in the next example. Okay, in example 9, we have this function, a cubic polynomial function. Let us use the Rational Zeros Theorem to get a list going of your possible rational zeros. Okay, RZT, the Rational Zeros Theorem, gives us 1, 2, 3, 4 times 2. It gives us 8 possible rational zeros. Now let's start using synthetic division and checking if any of these are actual zeros for the function. Let's start with the number 1. Now you have to be super careful here. We haven't seen this happen in a while. There's a missing term here. You have degree 3, you have degree 1, you have degree 0. What's missing is degree 2. So that's the reason why I put a 0 here, accounting for that missing term. All right, so let's do it. Okay, we found that 1 is not a 0, right everybody? But I want you to notice the signs in the bottom row of the synthetic division. They're all non-negative, right? They're all positive. They're all non-negative. In addition, notice that this c value, we call it c, is positive. I'm going to scroll back up on the screen and show you what the Boundedness Theorem says. If c is positive, which it is in our case, and every number in the bottom row during synthetic division is non-negative, then c is an upper bound for all the zeros. So in this case, what we just figured out is 1 is an upper bound for all of the zeros. All right, everybody, so 1 is an upper bound for the real zeros of this function, and this is what it means, all right? Here it is. Listen carefully. This means there are no real zeros that are greater than 1. For 1 to be an upper bound means there are no zeros that are greater than this number. Wait, what does that mean? Well, that means 2 is out, 4 is out, and 8 is out. I just eliminated 2 from my list, I eliminated positive 4 from my list, and positive 8 from my list because 1 is an upper bound. And 1 is not a 0 either, folks. So 1 is gone, 2 is gone, 4 is gone, and 8 is gone. All right, so this has eliminated all the positive possible rational zeros from our list. So now our list only has negative numbers in it. All right, so all the positives are gone, okay? Now let's check negative 1. All right, I'm ready to check negative 1 in my function, so let's see if it's a 0. Drop down the 1 and go for it. Now we find here that negative 1 is not a 0. Negative 1 is not a 0. And notice that this value here, which we call c, is negative, and the signs in the bottom row of the synthetic division alternate. Positive, negative, positive, negative. This means, and I'm going to scroll back up to the theorem here. Here it is. If c is negative, which in this case it is, and the numbers in the bottom row during synthetic division alternate in sign, with 0 being considered as positive or negative as needed. We don't have a 0 down here, so we don't have to worry about that. Then c is a lower bound. So what we just determined is that c is a lower bound, negative 1, is a lower bound for the zeros of our function. All right, folks, I want you to catch what has happened here. -1 is a lower bound for the zeros. Now, what does that mean? It means that there will be no zeros that are less than -1. So then eliminate all of the possible rational zeros that are less than -1 from your list. So -1 is gone, -2 is gone, -4 is gone, -8 is gone. Wait a minute. So the boundedness theorem helped me eliminate all of these options. So we just finished eliminating all the positive possibilities and all the negative possibilities. So in the sections that are to come in the future, I'll be able to teach you how to find the zeros for such a polynomial, because all of the theorems that we have on hand, all of the resources so far are not really helping us at this point, okay? So we're going to have to move on. We're going to have to come back to this example in a future lesson. Before we look at the last example, I thought you might appreciate some steps since this section has been really lengthy. So here we go. So what we do is we create a list of possible rational zeros using the Rational Zeros Theorem. Then you may want to consider Descartes' Rule of Signs to see if the list can be shortened. Begin synthetic division, okay? While you're doing synthetic division, keep your eyes open to see if the Boundedness Theorem can eliminate more numbers from the list after each completed division. So in other words, look out for upper and lower bounds. You want to continue with the synthetic division and finding zeros until you factor down to at most quadratic factors. But once you're at quadratic factors, you can stop the synthetic division and you can solve for the zeros using the zero product property. Sometimes, remember, that's where you set each factor equal to 0 and solve, using methods for solving quadratic equations as needed. Okay, so this is a great list to kind of follow. All right, let's look at our last example. All right, factor this cubic polynomial and determine its zeros. So here we go. Rational Zeros Theorem, okay? The Rational Zeros Theorem will say that any possible rational zero will be of the form P over Q. Here are your factors of the constant term. These are factors of the leading coefficient. All right, I put each of the factors in the numerator over 1. That's the first row. I put each of the factors in the numerator over 2. That's the second row. I put each of the factors in the numerator over 4. That's the third row. Now let me simplify all of these. Okay, everybody, I've simplified all of the fractions, and I notice I have some duplicates that I want to get rid of. So let's see. 1 is a duplicate. 5 is a duplicate. 5 halves is a duplicate. And is that it? Oh, 1/2 is a duplicate. All right. So my final list is pretty lengthy, right? So I'm definitely going to want to consider ways to shorten this. All right. So let's keep our eyes open. Now, you can try to use Descartes' Rule of Signs for this problem, and you will find out that Descartes' Rule of Signs does not shorten this list at all, okay? So what I'm going to do is I'm going to jump into the synthetic division, and as I'm doing synthetic division, I am going to keep my eyes open for upper and lower bounds. All right, I'm going to try 1 first and check to see if it's a 0. And it's not a 0. But what I do notice is that the bottom row is all positive. It's all non-negative, and so is 1. That means 1 is an upper bound. That means you can kick out any value from this list that is greater than 1, it will not be a 0. So because 1 is an upper bound, it eliminates any number that is greater than it from the list. So 2 is gone, 5 is gone, 10 is gone, 5 halves is gone, 5 fourths is gone, as far as the positive values are concerned. The negatives are still there, but the positives are gone. So you can see keeping your eyes open for an upper or lower bound is super helpful. All right, so maybe what we should try is a negative 1. All right, so we'll try a negative 1 here. All right, so what I see is that negative 1 is not a 0. Also, negative 1 is not a lower bound because these would have to alternate in sign, and they don't. It needs to go positive, negative, negative, and that pattern doesn't happen here. So nothing really interesting here other than negative 1. It doesn't work. Now, you've tried positive 1, you've tried negative 1. Don't try positive 2. Remember that positive 1 is an upper bound, so don't try anything that is greater than 1. How about we go negative 2? All right, let's check negative 2. Trusting that you're getting better and better at synthetic division. Oh, bingo. Negative 2 is a 0. Now that means if negative 2 is a 0, that means x plus 2 is a factor. Okay? All right, cool. And furthermore, let's not forget that the original polynomial is degree 3. Therefore, this represents a polynomial of degree 2. All right, very good, you guys. So what we can say is that our function can be rewritten as, now x plus 2 is a factor, and then your quadratic right here is 4x squared plus 8x minus 5. Now we should continue to factor this if we can. So then this can be factored, I think it can, as, let's see, 2x plus 5 out here. That'll give me 10, and then minus 1. Okay, that'll definitely work. So this is the complete factorization for my function, okay, right here, fully factored. All right, now all we have to do is find the zeros. But now that it's factored, I mean, it's downhill from here. You set each factor equal to 0, and you solve. This is a zero product rule. Subtract 2. Over here, add 1, and then divide by 2. Here, subtract 5, and then divide by 2, like that. So you found all 3 of your zeros. I'll write it in set notation, okay? So one of them is negative 2, 1/2 is the other one, and then negative 5 halves, okay? All of these have multiplicity 1, okay? They all appeared only one time as a solution for the polynomial. All right, everybody, I know this lesson was long. I know there was a lot in it, so you may want to take really, really, really good notes here. So I'm glad you stuck it all the way through, stuck it out to the end. I'll catch you in the next lesson. All right, see you later.